share my screen and start the presentation. So I suppose you all can see my slides?
Yes.
Good morning, America. Good evening to Japan and China and the western part of the Pacific, and then good afternoon to everyone in Europe. It's a great pleasure to be here today. And what I will do today is take you a little bit on a time history of quantifying earthquake rupture complexity from theory and observations. So I thought I'll take a quick look in the past, what has been done over the past decades, so to speak, and that will lead us to understand better the ingredients of rupture complexity, particularly the spatial variations of on-fault displacements, variability in what we call the rupture velocity, so how fast rupture moves over the fault plane, and then the local slip rate function. And I will discuss these items that are critical for us from an earthquake physics point of view in terms of constraints from simulations and observations. And I will finish off with a few remarks and open questions of what we need to address, in my opinion. So really, I will go back all the way to the 1960s and 70s when Archie proposed an omega square or omega cube model to explain the peculiar far-field observations so that the far-field spectra would decay in a very coherent manner. And Archie actually already described, we see this in the figure here in the second panel, figure 2, that the autocorrelation function of dislocation velocity, dislocation acceleration play a major role in understanding the observations. And shortly after, Brun and many other colleagues developed the first set of theoretical source models for point source-like ruptures to actually explain from a first order physics point of view how this omega square decay can be explained and what kind of source models are useful. And it turns out that these observations are still something we grapple with because we have to reproduce them in all our simulations that we do. About a decade later, Joe Andrews published a set of seminal papers in which he described fault slip on a two-dimensional plane. And so those two-dimensional slip function needed to show very specific properties in space and in the Fourier domain in order to be compatible with observations. So I'm showing these figures from way past then. There's a very simple slip. Can you see my mouse, Arben?
Yes, yes.
Okay, so here's a very simple penny-shaped crack with slip, and the stress function is very simple. Once we add a little bit of variation in the slip on the fault plane, we get very strong stress signals, stress heterogeneity. And Joe Andrews described this in a very elegant way in the Fourier domain, and I cropped the equations from his papers, where he says, well, the stress tau here in the Fourier domain K is related to the two-dimensional function of slip via this function K, which is a static stiffness function. And using this representation, he actually showed that the scaling exponent for the spectral decay for slip and stress can be written as K to the minus nu minus 1 or K to the minus nu for stress. And it turns out this nu has to be 1 to match the observations, or close to 1, of the far-field omega spectral decay. So this is very profound theoretical work back in the early 80s that led to lots of developments in this field. So, researchers have extended and applied Andrews' ideas. And I just want to highlight the work by Art Frankel from 1991, who basically developed a model in which he combines many elementary sources or sub-events in a very specific way to reproduce B-value observations and also actually the spectral decay. And the events, small and large, follow a power law distribution, very similar to like a Gutenberg-Richter type of relation, with the number of events for smaller radius being much larger than for large radius. And so using this approach, he actually came up also with a description for stress under fault. There are two profiles of such a stress function under fault with different, what we call Hurst exponent or scaling exponents here in the Fourier domain. And again, it turns out that the observations of an omega square decay put very strong constraints on how this stress has to look like. Namely, it needs to be self-similar without any scale dependencies in stress. So this work of Art Frankel actually led to a series of papers to define what we call a composite source model. So you basically, in a forward way, create a lot of small-scale ruptures, superimpose them, and use that as your source model to calculate synthetic seismograms. Zheng and Anderson did that. It was revived again by Anderson in 2015. And an additional way to do this was actually using the so-called K-square rupture model that Herrera and Bernard put forward in 1994, following the ideas of Joe Andrews. And with that, they were able to compute realistic seismograms out to frequencies of, let's say, 5 Hertz or so. A little later, I would say, towards the late 90s, we were in a fortunate situation that we had much more source inversion studies available. And by that, I mean, researchers have taken seismic and geodetic data to invert for the source process and the fault. And now we can use these rupture models to actually study what happened during the rupture. And there was a seminal study by Somerville to 1999 who characterized earthquake slip for 15 such rupture models. And on the left is kind of the processing they did on these 2D slip maps. They count asperities, so the large slip regions, and did some statistical analysis. Asperities for them were these rectangular features of high slip. And those were also prominently called strong ground motion generation areas. You count them, you compute how much the fraction of area of the fault is occupied by these areas, and that gives you a mechanism to create source models. Or they also actually did a very simple comparison with the K-square model for these few rupture models and found that it seems to roughly apply. So this is the work until about in the 1990s. And sort of 20 years ago, we were then in a situation where we had a large compilation of these finite fault rupture models available, not only 10 or 20, but hundreds or more of these finite fault rupture models. It turns out that they all show that fault slip is spatially variable, no matter if you're in a magnitude 7.6, as in the top figure shown here, or in a magnitude 4, as this little rectangle down there. And May and Barossa, as well as Lavallée and others, proposed that this slip heterogeneity can be described as a spatial random field. So in terms of an autocorrelation function in space, or the corresponding power spectral density, P of k, where k is wave number, in the Fourier domain. And just to illustrate what we mean by that, by these random fields, is there are 4 examples here of a Gaussian random field, then an exponential, a von Karman, or just a fractal. And they all show similarities, but they differ in the small scale details. They are appropriately described in the power spectral domain as shown above, and then they show different decay patterns. And that information is something we can actually compute for 2D slip inversion maps, and then try to match the power spectral decay and let's say estimate the correlation length or the Hurst number of these fields. So that was done, and the patterns emerging from the analysis of many of these rupture models is that this von Karman autocorrelation function best replicates the power spectra of these slip distribution. We see that the correlation length depend on magnitude. This is shown in the graphics down here. These are correlation length measured over magnitude. There's a clear scaling seen here, and we can derive approximate, let's say, empirical equations, how these correlation lengths change with size of the earthquake. It turns out the Hurst exponent is about constant for all the events that were analyzed at that time. with a leading to a fractal dimension of 2.3, so close to the theoretical prediction of Andrews or Frankel. And interestingly, this first exponent is also found nowadays in the rough fault images from, let's say, geological measurements. So there seems to be an interesting correlation here. So at this point, we basically have everything at our fingertips to simulate heterogeneous slip on a fault for kinematic rupture modeling or tsunami simulations, or even for estimating initial stress for rupture dynamics. So we assume the fault plane dimensions are calculated from source scaling, and we simulate random but realistically looking slip distributions as shown in the bottom here. These are 8 magnitude 7 realizations. The fault dimensions change according to the uncertainties in source scaling relations. And then we see these patches of high displacement on the fault. And a few years ago, 2016, Randy Levesque and others actually published a very interesting approach to Cahunen-Loewe expansion to actually drape these heterogeneous slip maps onto curved faults. And here is an application shown by from a paper by Melga and others. So that releases us from being constrained to planar surfaces to actually use even curved faults. So at this point now we have the slip on the fault, but something is missing to actually run calculations. We don't know yet where the rupture starts. Okay, so we have to constrain the hypercenter. We don't know how fast the rupture propagates, so we have to constrain rupture speed and also local slip function. And so these little animations here on the right are dynamic rupture simulations we've done in the past, and they show that by small changes in the initial stress field, you get very different ruptures. In the top, this is a small magnitude 5 event, it arrests early. In the middle, say almost essentially the same stress, breaks the entire fault, and in the bottom, the nucleation is far to the right and leads to a very complicated rupture trajectory. So how do we include all this into our kinematic simulations? And if we then look carefully at the local slip function on the fault, a couple of examples shown here. This is from a simulation. The yellow is the hypercenter. We see the very spiky character of the source time function in the beginning, and then rapid decay. But that actually varies quite a bit as you go to different points on the fault, as shown here. So this is what we need to capture in our simulations. So let's talk about the hypercenter location first. From many source finite fault rupture models, we noticed that the hypercenter location is not random. It is related to the slip or the stress on the fault. So usually rupture or general rupture starts on or very close to what we call a large slip region or asperity. So these are indicated here. These black contour lines outline the very large slip asperity. The red ones are large slip asperity, according to Mai et al. 2005. And so this is for the Loma Prieta earthquake. The hypercenter was fairly close to this red contour line, close to a large slip region. And this is actually consistent with energy budget considerations of rupture dynamics. But still, ruptures could nucleate at essentially any level of slip. And so this is the statistics of where the rupture could nucleate given the distance to the maximum slip or large slip asperity. So if we take this example again from Loma Prieta, the blue stars here indicate potential hypercenters for that slip distribution that will be consistent with the arguments I just made. So close to the large slip asperity. However, these red crosses would be hypercenters that are not consistent with energy budget considerations and these observations we have. So in essence, when you simulate a heterogeneous slip map on a fault, you should choose your hypercenter according to these conditions. Okay, so next we want to look at the rupture velocity. From finite fault inversions and dynamic rupture simulations, we know that it can be very variable. So here are 2 examples from finite fault: Archuleta's model for Imperial Valley on the top, Bouchon model for Izmit earthquake on the bottom. And the black lines are the contour of rupture propagation. And where they're close together, the rupture is slow. And where they're far apart, the rupture is fast. So with the fast rupture propagation, slow rupture propagation, and the same here. So it changes over the fault. Rupture accelerates or slows down locally. And that's a clear pattern we see in many dynamic rupture simulations, also shown in this simulation from a few years back. This is for a rough fault. We see the rupture propagating over the fault. It's kind of switched on and switched off, very complicated trajectory, sometimes slow, sometimes fast. And that's also visible in these very complicated contour lines here. And in addition to that, we may even have condition that super shear rupture occurs. That was found in Imperial Valley. In this domain, the rupture contours are spaced far apart, so very fast rupture beyond the shear wave speed, and same for the Bouchon model for ISMID. So how can that happen? I mean, how do we include that into our simulations for ground motions? And finally, I want to speak a little bit about the local slip rate function, which, of particular interest for us is the shape, the duration, and the peak slip rate, because the peak slip rate controls the radiation. On the right, I show sort of parametrizations that have been proposed and used in the past. This particular figure is from Lisa Tinti's paper. And what we know from simulations is that the shape, the duration is highly variable across the fault. So here's a set of examples from work of Guterres et al. 2003 and more recent from our work. Again, the yellow star marks the hypercenter, and this is a particular model here, a dynamic rupture model. The source time function changes drastically depending on where we are with respect to the hypercenter. Long and sort of subdued near the hypercenter, and very pointed and spiky and compressed in time as we are far away from the hypercenter. So this dynamic behavior we cannot capture with classical boxcar or triangular source time function. A truncated Kostov comes close, but most recently the Joffe function or regularized Joffe function has become very popular and widely used, which was proposed by Tinti and co-authors in 2005. And the beauty of that parametrization is that the peak slip rate of this regularized Joffe function is constrained by the maximum displacement on the fault, or at that location, I should say, and then two time constant, the acceleration time that's from onset to the peak time, and the duration. And so in essence, we have a very intuitive way to scale the peak slip rates based on the maximum displacement on the fault and some time constants. Okay, so at this point, I can sort of say, or can summarize and say, this is the current state of the art in kinematic rupture modeling. There are several kind of similar methods in use with the following workflow. We assume or we compute the source dimensions. The fault geometry is sort of known, and then we define a hypercenter. Typically, this is done prior to creating slip maps. Then we generate heterogeneous slip on the fault, potentially including some rake angle variations. And then we constrain the rupture propagation speed, VR, rupture speed, by using some of the scaling relations I showed between slip and rupture speed, or something. Mute. I was muted. Am I going over time?
Okay. Yes, Martin. And
I didn't hear any bells ringing.
Yeah, it didn't work for you. It's going to work for me.
Oh, great. Okay, so let me wrap up then. Sorry. Okay, so what I wanted to show is that we have some work to do. This is on dynamic triggering multiple rupture fronts and super shear ruptures. This is something we haven't really included into our simulations yet, so that the rupture front become discontinuous and actually super shear is allowed as well. And then these very compound multi-segment ruptures. This is something we know about, but our simulations have not been tackled yet. And so sorry for going over time. And with that, I want to conclude saying that we've only begun to get a handle on imaging and modeling rupture complexity. And the intricate rupture dynamics is only partially accounted for so far. So there is more work for us to be done. And with that, I close. Thank you very much.
Well, thank you, Martin, for your excellent talk. The second talk is titled